In this problem, it's given that there is a semicircular rod of radius r. There is a charge q uniformly distributed over it. We have to find the electric field at the center O. Now this problem is 2 steps difficult. That is 2 steps more difficult than this problem which I had uploaded earlier. I have explained it earlier. This is from JEE Main 2013. Why this is 2 steps more difficult? Because here there is a straight rod which has a uniform charge q on it. Here the rod is in a circle, semicircle. First thing. Second thing, in this problem we have to find the potential at this point. Here we have to find, in this question we have to find the electric field. Now the difference is the potential is a scalar quantity, so it doesn't have direction, but here electric field is a vector quantity, it has direction. So we have to keep in mind that we have to consider the direction also. Now I will explain this problem in comparison with the earlier problem. That will make the things more clear for you. Now see, if you remember how we solved this problem, what was our approach? Our approach was that we took a small element, sample element dl here, which had a charge of dq here. So for this sample element, first we found the electric potential at this point, which we call dV. Then to find the total potential for the whole rod AB, we integrated it to find V, the total potential at this point. The same approach will be used in solving this problem. So step by step, let me proceed. Here we took a sample element of length dl. So here also let's take a sample element of length dl. So this is the sample element. Now this sample element had a charge dq. Say this sample element, the charge on it, let me call it dq. Now how much will be dq? dq will be charge per unit length multiplied by the length of this element. Similar to this. So charge per unit length will be, total charge is q, total length is pi r. Here the length was capital L, so charge per unit length was q divided by L. But here this length is not given, radius r is given, so we know this is a semicircle. So total circumference is twice pi r, so half of that is pi r. So charge q divided by this length pi r is the charge per unit length multiplied by the length of the element dl. This is the charge on this sample element. Now for this sample element, the electric field here, this will be in this direction, because in the question it's given this is a positive charge q. So let's call it dE, the way I called it dV here. For this simple element that was potential, I called it dV. This is electric field, so I am calling it dE. It will be in this direction graphically. So dE, its magnitude will be 1 by 4 pi epsilon naught charge, that is dq, divided by distance square. The distance is the radius, so this is into r square. This is the dE. It is in this direction. Now another difference between these two problems is that here the potential was here, potential at this point was scalar, so we could simply add the potentials up. But here this direction, so the first sample element if we had taken here, so let's take another sample element symmetrically opposite to this. So at this point, let's take another sample element dl. So electric field at O due to this sample element will be along this direction. Okay, so if this is angle theta, so this angle is also theta. That is, this point, this sample element and this sample element are symmetrical. So this will be along, electric field due to this sample element will be along this direction. Now the net electric field due to these two elements, to get that we have to add these two up in doing by vector addition. So what we can do is we can make resolution of this dE, one along this direction, one along this direction. I am finding the components of the E. Now if this is theta, this will be theta, so that means this component will be dE cos theta, this component will be dE sin theta, right? So this is theta, this is opposite angle theta, so this is dE cos theta, this is dE sin theta. Similarly for this dE, this angle will be theta, so this will be dE cos theta and this side will be dE sin theta. So it's clear from the diagram that this component dE cos theta will cancel out with this component dE cos theta, and this dE sin theta will add up. So that means for this pair the net field is along this direction. For each element contributes dE sin theta. So electric field at this point will be along this direction, so that will be dE sin theta. So sin theta components have to be added up. Added up means to be integrated. So total electric field E we can get by integrating dE sin theta. Now comes the next question. In this integration we used the lower limit and upper limit. Here also you will have to use lower limit and upper limit. Now many students are confused about, or many students are not clear about how to give the limits in problems of physics. Okay, so I am explaining it in more details here. I think this will be helpful for you. See, in this problem, this distance of the sample element, I have taken it to be small l. So here we have integrated it after some calculations. If I take the earlier problem, we had integrated it 1 by 4 pi epsilon naught q by l dl by l. That is, our integration was on small l. Now how does small l vary? See, what will be what will be its lower limit and upper limit? How do you determine? It's like this. See, this is the sample element dl, which is at a distance l from here, small l from here. Now this sample element can be here, can be here, can be here, can be here, or here, anywhere. Okay, so when this sample element is here, the value of small l will be capital L, or you can say the smallest value that small l can take is capital L. That's why the lower limit is capital L. When the sample element is at this point, so distance of this sample element when it is at this end at B from this point, that will be twice L. So, or we can say the maximum value that small l can take is twice L. That is why in the integration the upper limit was twice L. So when we have an integration in physics problem, this is the way we have to think what will be the lower limit and upper limit of integration. Similarly, in this problem Now we have to do integration. So we'll have to have a lower limit and an upper limit. So let me first substitute dE with this. So this equation will become integration of 1 by 4 pi epsilon naught dq by r square into sine of theta. Again dq, if I substitute from here, this will become integration of 1 by 4 pi epsilon naught 1 by r square, this is r square, dq is q by pi r into dl, then this sine theta is there. So this is our electric field E integration of this. Now if we simplify it, what we get is integration of 1 by 4, this pi and this pi, so pi square epsilon naught r square and r, so 1 by r cube, this q is there, q dl sine of theta. Clear? Okay, now let's go to the earlier problem again. See, in this problem, when we arrived at this integration, there was only one variable dl. One variable dl in the sense, when the sample element moves from here or here or here, anywhere where it is, when it is at any other place, only thing that varies is the value of L. So we could integrate with respect to L. But in this problem, if you see, when this sample element, when it is here or it is here or here, what varies? Theta varies. Theta will be different. For this theta will be different, for this theta will be different, at this point theta will be different. So that means we'll have to integrate it with respect to theta. Now, but there is, in this integration, this term dl is there, so we have to replace dl and bring in theta here by some way. This can be done very easily. See, this small element dl, say it's making an angle d theta here. This small element dl, it has a length, so that length is subtending an angle d theta at the center. So we have this relation from geometry that dl will be equal to d theta into r, because length of the arc is equal to radius into angle subtended. So this relation we substitute here. So now if I substitute here, this will be 1 by 4 pi square epsilon naught 1 by r cube. Q is already there. Instead of dl, I write d theta into r, then sine theta. Okay, now next step. When you integrate, this is constant, so let me bring it outside. Q is constant, so Q comes outside. 4 pi square epsilon naught comes out. 1 r gets cancelled out, so this will be r square here. We are left with sine theta d theta. Now we will think about the limit, lower limit and upper limit. See, when the sample element is here, say if dl is here, then theta will be 0. So lower limit of theta here in the integration will be 0. Again, when this dl is at this point, theta will be 90 degree, but when DL is here, theta will be pi, 180 degree, that is pi. So theta will vary from 0 to pi. So lower limit is 0, upper limit is pi. So we'll write in the integration upper limit as pi. Now if we integrate it and substitute it, we get 4 pi square epsilon naught r square. Integration of sin theta will be minus cos theta, 0 to pi. When you substitute pi, this will become minus cos pi, that is minus cos 0, that will give us 2. So what we'll get is q 4 pi square epsilon naught r square minus of cos pi minus of cos of 0. So this will become 2, that 2 and this 4, it will get cancelled out. So our electric field E will be equal to q by 2 pi square epsilon naught r square. Now in the options it's given, directions are also given, j cap is given. So we have to now again decide what will be the j cap, the direction. See, the electric field, the net electric field will be in this direction. This is the negative j axis, negative y axis. So this will be minus j cap. So I can write here minus j cap. I am writing the j cap here and minus here. So this is option C. So the correct answer to this question is option C. This question is a difficult one. It has taken me quite long to explain everything. I think you should go through the solution once more to make everything clear. And let me repeat, if you have done this question before, then please do it first, then go for this question.